right, let's get started. Welcome everyone to the distinguished series lecture, which is the main event here at the Max Planck Institute for the Science of Light, bringing to you thought leaders in the science of light and related fields all across the world. So it's a great pleasure to introduce today's speaker, Professor Claudia Felser, who is from the MPI for Chemical Physics of Solids in Dresden. She is a well-known international expert on the design and synthesis of quantum materials and materials for applications such as solar cells or spintronics, and the current focus of her group is on topological quantum chemistry, so designing materials with desired band structures that have novel and curious properties like topological insulators and so on. So let me briefly tell you something about her career. She studied chemistry and physics in Cologne, where she did her PhD in '94 in physical chemistry. Then she had brief stays at the Max Planck Institute in Stuttgart and at CNRS in France. In '96, she became assistant professor in Mainz, where in 2003 she became full professor, and since 2011 she's been a scientific director at the Max Planck Institute in Dresden. And as of this year, she became vice president of the Max Planck Society. So she has won numerous awards, too many to list them here, but for example, in 2019, the APS James McGroddy Prize for New Materials. In 2022, last year, the Max Medal of the German Physical Society. In 23, the Condensed Matter Europhysics Prize of EPS, and she's a fellow of APS IEEE National Academy of Sciences in the US, and also the German National Academy of Sciences Leopoldina. So yeah, join me in welcoming Frau Claudia Felser, and we are really looking forward to your talk. Thank you for coming.
So I'm happy to be here, and I already saw the clean room, so very impressive institute, very nice building, I have to say. And I have to say, since you said something about my CV, Gerd and me, we were in the same gymnasium, so you didn't mention, but we both were in the same gymnasium in Hürth, so this seems to be a very successful school for a career as a Max Planck director. Okay, so I'm very excited about topology, so you already mentioned, but I'm also excited about chirality. This brings me also a little bit back to chemistry, to my very time back when I studied chemistry, and I hope, especially for light, chirality is also very interesting, and I hope I can inspire maybe some ideas for you guys, and maybe Florian can help me in the future to prove some things, okay? So I can give some question back to the audience, I hope so. And I have to say, topology, I think, is a totally new concept in condensed matter physics, and I'm quite sure we are still seeing only the tip of the iceberg, so there's still a lot of things which we could find in the future, and I think there's also very interesting science, I think, in other areas beyond of condensed matter physics, so I think many of the concepts are probably also interesting in other areas, and so I hope this is also a very nice way, the concept of topology, to get inspiration from other fields. Okay, so if we look back, so the field of topology has started with the discovery of the quantum Hall effect. I think when we started topology in 2007-8, when I came to this field, I didn't see the connection, honestly, but looking backward now, you understand things much better. So the interesting thing is what Klaus von Klitzing found in Hall measurement, if you go to very low temperature, so and we do many Hall measurement, so you can find this interesting behavior in the Hall resistance. So you find the plateaus, and they are quite exact here. So depending whether you measure rho xx or rho xy, you see zero resistance or this wonderful plateau. And the origin is if you make a nice two-dimensional electron gas. The samples are difficult to make. They should be not the best samples, I learned with time, and also from Klaus von Klitzing. So if you made the right concentration of charge carriers and so on, so you can have in a high magnetic field that you can localize all the electrons in the two-dimensional gas the magnetic field, but you have at the end very stable edge currents, which are spin polarized, and they lead to this very special behavior. But it was at low temperature and high magnetic field, later in graphene, also two-dimensional electron gas, simply in a simple layer of carbon. You could see this even also at higher temperature. This in this context, also the Nobel Prize for topology was given to Haldane, which was first a little bit surprising for me, because this was also based on a paper which was published in 1988. Even the boom of topology started much later, and this is maybe understandable now looking backward, because he predicted that you can find not only a quantum Hall effect, you can find a quantum anomalous Hall effect without a magnetic field if you take a magnetic material. And if you are coming from spintronics like me, it's logic, okay? Now, looking backward, I would say, why didn't I read in 1989 this paper? I would have immediately the idea of the material, okay? Because at this time, people made magnetic materials, magnetic semiconductors for spintronics, for semiconductor spintronics, and saying simply, what you do with an external magnetic field, so if you take a magnetic material, the intrinsic magnetic field is much higher. So it was logic from the materials viewpoint that Haldane had the idea, why not taking simply a magnetic material, and you should see the quantum Hall effect even easier, okay? So, but it's very interesting how science worked. So later, you think it's simple, it's trivial, you know? So because the intrinsic magnetic field of a magnetic material is so high, you should see a quantum Hall effect in a semiconductor. And indeed, this was the prediction. He simply has taken a very simple model. I can even understand as a non-theoretician this paper, and simply predicted something very simple in '88, which nobody recognized until later. I think the quantum Hall effect, anomalous Hall effect, was found in 2013, realized in a simple doped magnetically doped topological insulator. So people who are working on magnetism, they know not only the magnetic moment coming from the spin plays a role. Sometimes we see even in very small magnetic moment systems effects if there's a large spin-orbit coupling. And this was the idea from Kane and Mailer. So they thought, okay, they remembered this paper probably, or have read it earlier than me. They recognized what we can do with a intrinsic magnetic field in a magnetic material. Maybe if I take a material where I have a large spin-orbit coupling, I can realize also quantum Hall effect, like Klaus von Klitzing, by having this large spin-orbit coupling. They took graphene as a model system, which has a very interesting band structure, and I already told you graphene has also, as a monolayer in a gated sample, you can have the quantum Hall effect even at higher temperature, but they simply were looking for the quantum spin Hall effect, which is based on the spin-orbit coupling. So they took this very interesting material, which has this linear dispersion in the electronic band structure, and only this touching point, so this Dirac cones, which have very, very interesting property like ultra-high mobility, etc., and predicted that you can have this quantum spin Hall effect in graphene. The only problem is, with graphene, its spin-orbit coupling is small, because it's carbon. So nobody also like to look for the quantum spin Hall effect in graphene. So people immediately thought, okay, we should find it in a heavier element, like bismuth or something, because if we want to have spin-orbit coupling, we have to go to the bottom of the periodic table. Okay, but this paper in 2005 was the starting point, the real starting point for topology, which is, looking backward, a little bit surprising for me, because it was more or less wrong, because he took graphene. So the whole concept is now to generalize the concept of quantum Hall effect and this very stable electronic state in the quantum Hall effect to more materials. And for this, one needs the concept of topology, which is more or less stolen from the idea of mathematics, where people deals with surfaces, and this Gauss-Bonnet theorem, where you can calculate then this genius, which describes the surface that here a pancake has the same surface like a dice, and here we have a hole on the surface, has the same surface as a coffee pot, and in the same way here for the pretzels, etc. And if you translate it into electronic structures of materials, it's very easy. So therefore I liked it very much, because it's a very simple rule to understand. So if we have a normal semiconductor, we have a conduction band and a valence band, and the band gap between them in an insulator or semiconductor can be big if I have a strong bonding between the atoms in my solid, but if this bonding becomes weak, and this happens also if I have heavy elements, so then we can have a small overlap of my orbitals, which can even lead to a situation that we have the conduction band overlapping with the valence band, which is a semi-metal. And if we have spin-orbit coupling, so this is a forbidden crossing, so the spin, the spin is not a good quantum number any longer, and so I can get this new semiconductor here, which has a part of the conduction band and the valence band, and vice versa. And this situation is topologically distinguished, so I can say this is like a trivial pancake, while this is a donut. And because we have these different parts of bands here in the valence and the conduction band, so I get naturally surface states, and here we have the similarity to the edge states in the quantum Hall effect, and they are spin polarized, and they are very robust in the same way as the edge states in the quantum Hall effect is robust, which means I can have here a semiconductor and insulator, which is insulator, this is my crystal, and I like to grow crystals, as Florian said. So it's really insulating, while this insulator, the topological insulator, has this protected surface states with electrons where spin and momentum is locked for the different spin directions, now in three-dimensional, very similar like the quantum Hall effect. Okay, so, and this was interesting theoretical prediction, but as somebody who knows material, you immediately have many ideas, and many people had also many ideas. So the first realization was then people were looking now for elements, but there's no element which has such a band structure, only if you dope bismuth with something else, so it's a heavy element, bismuth on the bottom, but there are binary compounds which have this property. But what is also nice and interesting is if the spin and the momentum of an electron is locked, the electron is also chiral. And so when people predicted this, I remembered all my nice Häusler compound, which was in my first part of the career. So people recognize that this is this electronic structure you find for mercury telluride. So if you have silicon, you have a situation like this. You have a normal semiconductor, but if you go to 2,6 semiconductors, so you have, for example, mercury telluride or selenide, so they have heavy element, you have exactly this situation. And the first prediction was for this. So we like then even to work with 3 elements, and this was the story how I came into the community. So I simply looked into my Häusler compound, and this is here simply the band gap. So if it's the red over the blue band, it's a positive band gap, and here have this band inversion, it's a negative band gap. So I have many of the compounds which are normal semiconductors, but I have many compounds which are showing this inverted band structure. And the nice thing is many of these compounds are magnetic, also superconductors, so they are interesting for many reasons. So more or less, we can realize in this ternary compound with these 3 elements, the same what you know from silicon or from binary semiconductor, like here for this 3,5 semiconductor like gallium arsenide, you can simply get exactly the same band structure in this ternary compound by simply counting the electrons. So realizing exactly band structures like this, or band structure like that. So which gives you many, many, many possibilities to make this topological insulator compounds. So nowadays, we investigated all existing inorganic compounds, whether they have topological properties or not. And it's more or less, that from all the 250,000 known compounds, more than 25% are topological. So many metals are topological, but maybe the topological properties are hidden. But there are also many semi-metals and semiconductors and insulators who are topological. And even in magnetic materials, there's even also an inflation of topologies. Then you can say, is there any impact on topology if topology is everywhere? Indeed, so because many of the properties, and I don't talk about magnetic materials, many of the properties we didn't understand, we found sometimes are now much better understood under the viewpoint of topology, or we find even interesting properties like giant responses to like super thermoelectric materials nowadays using the concept of topology. So it's based on the theory, so Florian knows we are calculating how nowadays the topological properties by calculating Berry curvature, and we can see whether we have super thermoelectric materials or, and probably also non-collinear magnetism can be understood by using the concept of topology. So it unravels a lot of new properties in materials based on this new concept, which is quite simple, but it's interesting. And so now it's more or less, you find more or less in all non-magnetic material, if you allow even doping, you can tune it to the right electronic structure to find the best topological material. And nice is really, these properties are very strong, very protected, because as I said, if spin and momentum is locked, so they can find what people in spintronic love to have 100% spin polarized current, so a current which is only based on the spin and not on the charge of the electrons, which allows even a transport of spin information without transporting charge, which is much more energy, less energy consuming. So this is a totally new field. So there's still a long way maybe to really work on the electronics of these materials, but I think many of the simple properties which I like are found. Why is it so interesting that if we have spin momentum locked and this chiral electrons, and why is chirality so interesting? Because chirality is a fundamental broken symmetry and plays also a role in many other areas of physics and in chemistry. So one of the fundamental questions, for example, of the origin of life is not solved, and it's also based on chiral molecules. So if I have a molecule and carbon with 4 different ligands, so it's chiral. So I can make 2 molecules which are distinguished by their catalytic activities and by matter interaction, but not by energy or by other physical properties. So because we can have 2 different molecules which look on the first view the same, but you cannot, it's like the right and left hand, you cannot bring them to coincide, so they are distinguished very similar like our electrons when spin and momentum is locked. And there was a really nice, interesting workshop on chiral matter, which was bridging this question of chirality in matter from high energy physics to astrophysics to condensed matter physics and to organic chemistry. This was during Corona, this was only the European part of the team, which is also most favorite interest, or one of the favorite interests of here Frank Wilczek, who is maybe well known to you as a community, and also some axion physics is hidden in this topological material. So I give you a little bit of taste why this is so interesting and whether this maybe can be, in some sense, making a nice bridge between chiral molecules, topological materials, and eventually also, and this was also subject of this discussion, like the weak forces and the beta decay of cobalt atoms in a magnetic field. So also here we don't know how this has happened, that we all are made only by one kind of chiral molecules. So the origin is not known. What can be the origin? How did it start, you know? So far, people like Ben List, with whom we also work, they put structure chirality in to get structure chirality out, which means we do a catalytic reaction with a chiral catalyst to get a chiral molecule. And chiral molecules are extremely important also for pharmaceutical industry, because if you want to treat cancer or Alzheimer's, you need chiral molecules, okay? So therefore, this is a big business, and I think it was not, maybe it was even related to our workshop why Ben List got the Nobel Prize a year later on his work. But it's still an open question. And I want to talk a little bit about the chiral anomaly, so these topological materials which have this very interesting electronic structure. This Dirac-kind electronic structure can also serve as model system for the asymmetry between particles and antiparticles. This was also subject of this workshop. So if we solve the Dirac equation for quantum fluctuation, we can explain under certain circumstances that we have this chiral anomaly. If we have this chiral anomaly, that we have an asymmetry between particles and antiparticles. So why we are existing with particles, electrons, and not positrons in a way where we can do this investigation simply in this condensed matter system and seeing it for electrons and holes. So this is based on semi-metals, so beyond of this topological insulators, and therefore so many compounds are topological. Interesting is that we can have also semi-metals and metals, and this can happen if we have a certain symmetry in our crystal. So we can have this. So here I told you we have this overlapping of the conduction and valence band, and there's a forbidden area. So due to this forbidden area here, we can lift this degeneration and we get a topological insulator. But if we have crystals who have, for example, rotation symmetry, we can have not the whole area forbidden, so we have still some parts of the area which stays connected, so degenerated here, and this is the semi-metal. And we have two kinds of semi-metals, Dirac and Y semi-metals, so depending on the symmetry. If we have no inversion symmetry or magnetic materials, so we have this at low symmetry points, and these are so-called Y semi-metal. And these Y semi-metals are very interesting in the context, making then the bridge to axion matter and chiral anomaly. And the reason for this is then that we have this linear dispersion here, these two Y points in a material, and they have different chirality in the bike. So I think the theory for this you can ask Florian. So we are looking for this material. So as I said, this must be topological material which has this linear dispersion, and they have non-centrosymmetric structure, or they are magnetic, and then they have the situation that we have this crossing points here, and they have different signature signs here in the Berry curvature. So they act here more or less like magnetic monopoles, like source and sinks. And we see then in this material also surface states which look like a Fermi arc. It's a little bit different from a topological insulator. But this material got a lot of attraction because the solution of the Dirac equation is very interesting also because there are hypotheses about the existence of dark matter, for example, related to wild physics. Okay, and the reason is that this is from Wikipedia. You see, you don't even have to have a physics book at home to understand which materials you have to look for. So this is a parity violation. So the chiral anomaly is that you can have the situation, as I already mentioned, you can get an asymmetry of positive and negative charged particles based on the chiral anomaly, and this is only possible in a quantum world. So, and could explain why the universe exists, there exists more matter than antimatter. So this experiment is also done in high energy physics, so people do heavy ion collision to prove the chiral anomaly here, and recently it was done also in solids. So we cannot measure the asymmetry between antimatter and matter, but we have quasi-particles, so our dressed electrons in a solid, so to say something about the real chicken. So I don't do the chicken experiment, only the quasi-chicken. And the important equation is here, coming from high energy physics, sorry, I don't have the original references here, is that you have to apply this E dot B term to observe the chiral anomaly. I skipped one slide, sorry. So, And this means in our experiment we have to take one of these vial semi-metals, and we have to apply a magnetic field and an electric field in parallel, and so we should see then a specific response which was predicted then by condensed matter physicists to show that we see this analogy in a solid. And you can also do the so-called axial gravitational anomaly. This is an experiment which people try to investigate in astrophysics. It's more or less the same equation, so only if plus applying a temperature gradient, and it's related to entropy changes. But this was a prediction by theory, and for us was simply interesting, can we find the right materials and can we do the right experiments? And indeed, so the idea is here that you can change here the number of electrons and holes in our solid by doing exactly this situation, but only if the magnetic field and the electric field is parallel, or you have a change in entropy. Anyway, so which means we have to switch the magnetic field to switch the chirality in our solid, and this is the experiment. So luckily, it was after people looked for this white semi-metals, and as I told you, this topology is hidden in many of the materials. This material was found, which is a binary compound, tantalum arsenic. This was the first compound where really the experiment could be done because it was a simple compound, it was easy to make. And the first step, what you do normally in condensed matter physics, then you look whether the drawn picture, the nice picture, so nature likes nice picture, but they have nothing to do with reality. Anyway, so you can say, is my nice picture really what I see in reality? And for this we do Ingerisser photoemission, so we can simply see the band structure, energy versus momentum. Sorry, this is was my German slide. Okay, energy versus momentum in photoemission spectra, and you see here, you see really this nice linear dispersion and this double peak, if you want, in the photoemission of this material, and nothing else. So it was not a. And then the next step was simply to look for the surface state. So we took a series of this compound and increased here spin-orbit coupling, and you see spin-orbit coupling has an influence on the electronic structure. So you see a nice splitting of the bands based on the spin-orbit coupling, but also my Y points are far away from each other, and this is what then is the calculated surface state, what you expect, this Fermi arcs, and this is what with photoemission measured the surface state, and you see nicely how this agrees really with the increase of spin-orbit coupling. Anyway, so the experiment which we wanted to do, and was a nice and more interesting experiment, was looking for the chiral anomaly, and so we did this typical Hall measurement. So the magnetic field is perpendicular to the current, and you switch this direction, and you see this was the prediction that you switch the sign in the conductivity. And we did the same experiment for the thermoelectric transport. This was a nanoribbon of niobium phosphide. So it's a quite difficult experiment, but anyway, so you can see this also. So we were very happy, but it's a transport experiment. And you can imagine, we had a long discussion, it's always indirect, so we only see the quasi-chicken, not really the chicken. So we are still looking now for an experiment where we see nice quantization through the chiral anomaly, right? And we have some ideas, and one of my theoretical co-workers have an idea. Anyway, we had IBM as a co-worker, and they have a very nice PR department. They can maybe even make better pictures, and we brought it with us even to the New York Times. But it's not only here in our niobium phosphide. So this effect is even seen in bismuth up to 200 Kelvin. So if I want to make the connection between the chiral anomaly and the origin of life, eventually I need it at room temperature. So this is a quantum effect which is even there at higher temperature, which is quite nice. Okay, so, and you see it also in magnetic material. Here you see a real band structure and this nice overlap. So you see these nice crossing points, like if you do a real band structure calculation, and here we saw also in this Kagome lattice a nice negative magnetoresistance effect. Okay, so then after looking for this chiral anomaly in Y semimetals, which are structurally not chiral. Only the electrons are chiral. We did some discussion also, if you have so many topological material, what happens if I have a chiral crystal? So I already have chiral structure. I told you this is maybe less exciting for the chemist, putting chirality in, getting chirality out, but maybe we can learn from this something to even come for better experiments and also for our Y semi-method to prove the chiral anomaly even maybe better. And 30% of all the crystals are crystallizing in chiral structures. But there are only 10% of the crystals known to be chiral. So one problem which we still have is like, we very often have more interesting crystals than we know, because so far the investigation, the characterization of the crystal is not good enough, or was not done with enough care in the past to really see the properties. So, and this is even more interesting because the Dirac equation, so the Dirac, of the Dirac solution, the Dirac equation is a equation, and the Weil equation are having high energy and astrophysics counterpart. But what happens if we see in a solid maybe something beyond? So despite of the Dirac equation, which is simply the linear dispersion, but it's not chiral, we have a fourfold degeneration. The Weil I already explained is very interesting because we have this chiral crossing point with the chiral electrons, and they show the chiral anomaly for this reason. So we can have more than two-fold and fourfold crossings in a solid, but we can also, in a chiral solid, we expect even that we have also, again, this chiral fermions in a chiral solid, but here we have it not at the same energy in our band structure. So if I would bring them, if I would distort my Y semi-metal in a way that it becomes higher symmetric, it would so annihilate this different chiral Y points and generate a Dirac point, while the Dirac point in a magnetic field would go to Weil. But here, this cannot happen because the different Weil points are at different energy. So this was first a theoretical paper where we thought maybe we should find something. Can we find then again a material which shows these very interesting properties, and what are the expected properties beyond Dirac and Weil? So first of all, Carlo Benacker was very excited about this because he recognized that we would expect then particles which are not existing in high energy physics, and even Heisenberg has speculated about this. If one could put a guitar on a universe, so sometimes solid state chemists are useful, so we can put guitar on a Dirac world, so then you can find even some new particles which are more interesting. So we're still looking for the new particle physics in this, but okay, so far this was simply what made the referees happy, seems to be. Okay, so then you can grow all these materials, and one thing is, it's if I want to make a chiral molecule, why is this such a big business in pharmaceutical chemistry? It's because if you simply try a chemical reaction, so because the energy of both chiralities is exactly the same, and the molecules look very similar, so you end up always with exactly 50-50. Okay, and this was also why Ben List got the Nobel Prize, because he found very tiny little chiral molecules without metals, which could lead, but if we put them in as a catalyst, which could then lead to one chirality. Okay, so if I want to make chiral crystals, I have the same problem. Okay, so energy-wise, there's no distinction between this chirality and that chirality. So they are very difficult, and this is what a part of my group now is trying to find ways to synthesize homochiral crystals. Because if you want to do physics of chiral topological material, we need a homochiral crystal. You know, if I have both chiralities, it's very bad. It's like giving you the wrong medicamentation against Alzheimer or cancer. If you have both chirality, one is poison and one is helpful, so you might die. Okay, anyway, so we were lucky in some compounds. We really were able to grow these homochiral crystals, and we can also do structural investigation to see really whether this has this chirality or the other chirality, so they look very much like a DNA, this B20 structure, and we can make quite a few of this material. And so the prediction here was that instead of this property, this electronic structure, we get two kinds of electronic structure which are distinguished for each chirality. So they are really a little bit more different, even like the chiral molecules. This is very interesting, this topological, because depending on whether I have this chirality or that chirality as a crystal, I have different kinds of surface state, which are also chiral. And I have different Berry curvature signs in the different chiral crystals, and I already told you, so these crossing points are at different energy. And so there was a prediction also that we can find the quantized effect, so the quantized circular photogalvanic effect in this material beyond of other interesting physical observation. Okay, so this is more or less the two different chiral crystals is more or less a moment in the life of wild semimetals, but the effect is here much larger than what we would expect with the E dot B term by applying this magnetic field in a wild semimetal. Okay, so then you have to find the material. I already told you we have this B20 structure, so this is a band structure of this material, but the two different chiralities have two different band structures, and we have here this is at the air point, we have a four-fold, a six-fold degenerated one, a six-fold degenerated point. At the gamma point, we have this other point. They are looking much more distinguished than in wild fermions. And we can see again, and here you see if you take different chiralities, they are totally identically the band structures. This is also the problem of the molecules. They have the same energy diagram. But here, we can distinguish them by the phase. So this is a nice thing. So they at least are more distinguished than simply in the molecules. So they have different Berry phase for the different gamma and R points. So you can then do again this Ingerisov photo emission, and you see really here this nice degenerated point, the four-fold degeneration and the six-fold degeneration. You can also see the surface state for the two difference, but it's very difficult to see, sorry. This is because it's a surface state with photo emission. You have to believe it now. And you can also prove that these compounds have this very nice, this is more for the expert for here, that you can have Florian, that you have this high Chern number by looking for the splitting of the bands and the slope of the electronic bands in this chiral material, so that they have different signs of Chern number in these different chiral crystals. Okay, so we can also shine circular polarized light on the crystals and then see the band structure. And here we calculated the Berry curvature, and you can see, you can really distinguish the right-hand crystal from the left-hand crystal. So we are very excited about this because the Berry curvature is proportional to the orbital angular momentum. And the nice thing is this orbital angular momentum eventually gives us a scissor to maybe let chiral molecules talk to chiral crystals, or later also to wire crystals to maybe to maybe make only one kind of chiral molecules. Okay, so you see they are also like left and right hand. Okay, so then there was this prediction of the quantized circular photogalvanic effect. We see a kind of plateau here, but it's not as nice as the quantum Hall effect, so we still have to work on the materials, and we think here it's related that why we have still a few other bands crossing. You saw our spaghettis were a little bit too busy. We have to find maybe a better material here still. But this is the goal, to find really quantized effect at the end of the day. And you can find it in other materials similar, so you can find this here chiral surface states in other groups. We worked with other groups too, and interesting surface states. Anyway, so what is interesting then, because I like also chemistry, we looked whether we can have an interaction, and these are first experiments with these chiral molecules. We choose dopamine because as you can buy nowadays, we use also other molecules, and we did a simple reaction here, and we can distinguish depending from the chirality of our crystal. It likes especially one chirality of molecules, and this the other chirality like the other kind of molecules, which is not so surprising since our surface is chiral. But what is very interesting, and this I like very much, is that our chiral molecules react also on an external magnetic field, so it shows, so we can measure in a magnetic field, and this topological materials show very strong response on a magnetic field. So if our molecules shows also strong response on a magnetic field, so we think we can make topology talk to our molecules. So these are the first experiments, and we are working with Ben List a little bit on this. This was a long time before he got the Nobel Prize, by the way. So he started to be interested in topology in 2018, and so we're looking now for interaction with molecules and this our topological crystals. But the next step now is also what is exciting is that recently other people found that you can make materials which have a chiral charge density wave. This for us is again super exciting, so which means we can use chiral light or a magnetic field to switch on this chirality or that chirality. Okay? And there are even some examples where you can do it at room temperature. So this I like. Because our dream experiment at the end is how can we put our chirality in and get chirality out, structure chirality in and get chirality out. Anyway, this is also a nice direction, and there are quite a few materials where you can find this gyrotropic electronic order. So people are discussing, is this only electronically? So do we only switch on the electrons in this direction or in that direction? But I think there must be also structural distortion related, because I would say honestly, the electrons cannot only do what they want without the atoms and the phonons following them. Anyway, it's very interesting because you can tune and off and on in a solid with light, chiral light, or with magnetic field. Okay, so we did this also for one of the compounds, cesium, vanadium, antimony, together with Philip Moll. So we could really show that we see here a switchable magnetoelectric effect in this material. This material is not chiral at room temperature, but if you lower the temperature, here you can switch on this different and off this different chiralities in the magnetic field. Here you still need quite a little bit of magnetic field, but there are other examples, I hope, where we can do it at lower. But this would be very interesting here. This is here the magnetoelectric effect, which is because this could be also a very nice way maybe to have interesting interaction between molecules and solids. Okay, I was too fast, no? But I have 45 minutes. I thought, okay, so I hope I gave you some impression that topology is a very interesting field, and that there are topological insulators, white semimetals. I still think that the white semimetals is a very interesting system where we really should look how we can prove parity violation in this model system in condensed matter, and I would like to see some quantized effect which would be more convincing. Despite of this, we have also done some axion work on this, but I didn't show this. And I think also these new fermions are interesting, these chiral materials beyond Dirac and Y fermions. So one of the challenges we are doing now is really how to grow really the enantiomeric pure compound. And for catalysis, we're very interested in the chiral surface state, but also that we have this distinguished orbital angular momentum, so to go maybe in direction of catalysis and enantiomorphic absorption. Anyway, it's still also interesting to investigate the physics behind this, the interplay between structure topology, and can we maybe find system where we can put our chirality in and get chirality out. So, and yeah, this is our vision. So more from this non-local transport, doing the catalysis here, and maybe looking for chirality plus magnetism. Is there a relation between topology and the magnetic structure I already mentioned. There are a lot of non-collinear magnetic structures in physics. Nobody knows why we have this non-collinear magnetic structure in which system, but this might be also related to the reciprocal space, to the momentum space, electronic structure, and probably to topology, and what happens in the future also in direction of superconductivity, because if you have a chiral crystal structure, do we find interesting superconductors, maybe topological superconductors for topological quantum computing, etc. Okay, thank you very much for your attention. Okay.
Thank you very much for this fascinating talk, Claudia. And I'm sure there are questions, and I see the first one.
Thank you very much for this nice talk. I have a question about these photos of the crystals that you've grown, that you showed, the palladium, something like, do you have an explanation of why do they look so different, the left and the right one?
Yeah, this is maybe why we were able from these crystals to grow different chirality poor. So I think it must be related to the kinetics of the growth process. So interesting thing, in this material we can simply grow them for the melt, and we get 30% of one chirality, the ugly ones, okay? And 30% of the 70% of the nice ones, and they're homochiral. And it might be with the growth condition, you know, so you have multiple, so it starts maybe at multiple points and it tends to one chirality, and it's interesting, but we don't understand, and it's not simple logic, because you would expect always to have a homochiral crystal. Not a homochiral crystal, exactly a 50-50 mixed crystal if you don't use external forces. So in this one case, it's really possible without external forces. So sometimes you can grow these homochiral crystals by the help of light in a few cases, but also this is not really systematically understood and investigated. So we are doing this now in a more systematic way. The chirality.
Okay, okay, thank you.
Very good. But I don't understand it. Okay. Okay.
So, Claudia, I wanted to ask a few questions that maybe have something to do with the previous one in a sense. Could you explain a little bit the difficulties in actual fabrication? And you showed a few cases where it looked like you were drawing out a melt, but I imagine that MBE is an option or not?
Yeah, absolutely.
So can you say a little something about the difficulties in growing the material and then characterizing them to see what you've actually done?
I was a little bit fast here because I thought I'm not sure whether it's so interesting for you. But indeed, it's not really fully understood. So some people did something in organic crystals. So there are different ways. You know, if you simply grow it in a melt, and this is interesting because they are all made by melt, okay? So you don't have seed crystals. So you don't start with one chirality. You simply do it, boom. And interestingly, some of the crystals really, this is the left-handed one, as for example, and it's really much uglier than the right-handed one. So it happens. They grow homochiral. So while other crystals like cobalt silicide, so they always grow as a mixture. But the domains are quite big, okay? While other crystals like iron germanium have small domains. So they have domains that we really can get a part of a crystal out, which has, so in photo emission you can distinguish them, or in some way you can distinguish them. So it's really a field where, so in some sense you can, if you use the seed crystal, so here you can also play a little bit with the composition, put a little bit iron in, do a seed crystal, then you can grow one homochiral crystal. But we have no systematic understanding, we have to say. We try also tellurium with chemical vapor transport, which you can grow in chemical vapor transport. Also this you can grow. There you can try to put some chirality in to get chirality out, which means in organic crystals they sometimes put like DNA molecules in and get then a chiral crystal out. So see this, but in the original sodium clathrate, in the original experiment from Pasteur, he simply rotated steered the crystal and he got one chirality, steered in the other direction, got one chirality. So what we are building now, a crystal growth facility which is rotating. We're building one in a magnetic field, because some people think, and this is this chirality-induced spin selectivity, where people now want to have SPP, which I think is super extent. They say that the spin might influence the chirality of the molecules and maybe eventually. So this would be cool, because then you would put non-chirality in and get chirality out. So Ron Marman is very famous for this, and we see evidence, even for we can make nice catalysis and so on by using the spin. So if you have this spin direction, you get this chirality. You switch the spin direction, you get the other chirality. It's amazing, no? But it's also not really shown in a big way. So what we try to do also, people do it in SDM or in a small, tiny physics surrounding. We always want to do it, boom. So it works always, reproduce all the time. Yeah, but it's a good question. So how can we characterize this? This electron backscattering diffraction is a way to characterize bigger areas, you know. So you can screen this and see that this crystal, but it's surface sensitive. But we still think, okay, anyway, our photo emission is also surface sensitive. And you can do, if you are very good, you can also eventually X-ray, but it's volume sensitive, but it gives you only a very small area, you know. So if you can, maybe you're in optics, so he has this to do. Okay, I want to have quantized effects for wild semi-metals. I have some ideas, and one of my theoreticians already has some. But here is maybe, it would be good if we have something in optics, you know, to characterize the chirality of a crystal. So, because this you can have in in transparent crystals, okay, but not in this crystal. So it may be a question of the wavelengths, but this would be cool. You know, because since we make a lot of crystals, you can imagine this takes forever. You know, take every crystal, do E-beam, this electron backscattering. Sorry, it takes forever. Yeah.
Maybe I can ask a question. So you repeatedly showed these nice pictures of a 3D cube representing the material, and then the surface states, the two-dimensional surface states on top of the 3D. How difficult it is to actually measure these? I mean, I know, of course, the 1D edge states on the 2D materials, but how difficult is it to measure these?
So in photo emission, you see easily the surface states.
But if you want to have transport,
in transport, it's more difficult. But people did, for example, so one thing is to make very high quality crystals, and I would say we have very good high quality crystals. So then you really have to have the bulk insulating, and then you see. So I think I didn't show here. So very often in transport we have the resistance goes up, and all these wild semi-metals and all these topological insulators have a plateau. And I would say this is a plateau is related to the surface state, but it's difficult. Okay, so there were some. So what might be a way one could do what also Klaus von Klitzing's group does. They measure the potential, you know, and then they see that the potential at the edges are different from inside. But even they say the picture of the nice edge states are not really what they see if they measure the edges, you know. Okay.
Okay, very good. Are there more questions? Yeah,
You were talking about the chicken and the quasi-chicken. So the electron positron in the vacuum and the electron hole in the. Now in the vacuum, this is Lorentz invariant, and in the crystal, of course, you have the lattice. So this does it mean that? So
we are also Lorentz invariant, no? So I can ask him, my theoretician. I brought my theoretician with me.
Yeah, but the lattice can be stationary. I think it should be. I think this should not be Lorentz invariant. Of course, you have the periodic boundary conditions, and this maybe affects the momentum transfer, maybe. And so I was wondering.
I don't know. Should I?
Yeah, I ask you.
Problem is that true Lorentz invariance applies to all fields and all interactions in the same way, whereas here you would have it for the electrons, but suddenly the phonons do their own thing with a completely different speed, and the electromagnetism does its own thing, and as soon as they come in, then it doesn't behave like your true Lorentz invariant relativistic universe, I would say, right?
Yeah, might be. So you see it only in a special, it's true. The question is, but it's a good question and a good inspiration. I was also thinking, with all this chiral stuff, do we see something in the phonon, special behavior of the phonons? Are they also chiral and stuff like this? We are trying to understand this. And yeah, how does it influence also other particles or quasi-particles?
Right.
So speaking of things like phonons, there were mentions of temperature here and there, and you said sometimes this also works, it even works at room temperature. So can you say something about the temperature dependence of all these effects and how sensitive they are? What's the critical temperature that you usually need to?
So it depends on the material. If it has very clear band structure, and this you can design by bismuth, then you have also, it's a little bit like the graphene. Graphene shows the quantum Hall effect also at higher temperature. So in bismuth, we can have few millions of, in our crystal, few millions of mobility. Okay, and then we dope it to the right, then we see good temperature behavior. Otherwise, it's more a low temperature effect, but not a low temperature effect like the quantum Hall effect into DEC maybe, so it's still living up to 10 Kelvin and so on. But you can design clean materials with simple band structures anyway, but they are not like every material is topological. They are very rare, okay? And you have to really be careful with the crystals. So I still think we have to find oxides. They might be even better. And with, yeah.
So when I see things like this as a non-condensed matter physicist, I immediately have to think of kind of like Feynman's idea that let's just take atoms and put them next to each other and make our own material.
Yeah.
Is this something that theorists are working on? You just look at your periodic table and say this and this and in this structure, and let's put it together and calculate and see what kind of a strange topological effect you get?
I think this is like, so one thing you can see many topological effects also in metamaterials. If you simply care about the symmetry, and one of the essential things is symmetry, okay? But it's true. But I think so far we are still relying on density functional theory, and they have their limitation, for example. So the ideal material, so for example, the ideal representative for the axion was the origin why Frank Wilczek was so interested. I could have showed this also. So you have a wide semi-metal. If you have an ideal wide semi-metal, I would say it always opens a band gap. Okay, so because if you only have these two touching points, so energetically it's easy to open the band strap, but then if you can bring it back, you show like the sliding mode and some physics of the axion why you can prove that this equation might make sense, and if you show this axion physics, so somebody like Wilczek hopes more to find the axion in the universe, you know. But you have to design the ideal material, and this is true. It's yes, we can to a certain extent do probably also with machine learning in the future to design the right material, because you have to find stable material and not only the prediction, and you have to take into account also nesting, correlation effects and so on, because they might change. So it's possible, but it's still, now the next step probably, it's a very good idea. But it's also nice to have this metamaterial or this photonic crystals, because you see simply so some general features what you can expect then from a solid and a condensed matter system. But also people do topology now, like Monika Eidelsberger in boson gases. Yeah.
Regarding to the central picture here on your slide, you mentioned that it's kind of a bit tedious to do the characterization, and maybe one could do something with photonics. So I think with angular momentum, spin states, left-right circular polarization. It should be more or less straightforward to study this. I'm surprised it has not been done.
Not for crystals which looks like metallic, like silicon or like metals, you know. So with transparent metals, it's easy because you take chiral light and you see something of these molecules in a solution you can identify by optics. But with this reflection, you need to be
metals. If this is chiral material, it could be that the attenuation is different between left and right circular, for example. Maybe that would be.
This would be interesting to see some differences, because this would make our life easier. You know, if we could have a fast because it's now like Ben List is now interested in our crystals, and Ferdi Schütt is destroying all our lovely synthesized crystals in his ball mills because he needs big surfaces for catalysis, you know. They are busy growing these wonderful crystals and they put it in a ball mill to get a lot of surface. So having a faster way to characterize. So because it would be, as they say, it would be already cool if we could do catalysis with these homochiral crystals.
Just send us a piece of one of your wonderful crystals, big enough so that one could do optics on it.
We can send you one chirality and the other.
Yeah, perfect.
Okay, good.
Hey, I think if there's no further urgent question, then let's thank the speaker again at this point. Thank you.
If you're working with Florian and you have some idea about quantized effect in Waldsemer metals, I'm happy to get the ideas, okay? And if you have ideas like here, then you should come up, and I'm happy also to send you crystals like GET and others. Okay.
Very good.